Section 3.2, Centripetal Acceleration. In this section, we're going to talk about uniform circular motion and acceleration of the object that undergoes this type of motion. The hammer throw is a Summer Olympic track and field event. The hammer, a heavy metal ball attached to a wire and handle, is thrown by an athlete furthest distance possible. The athlete will move the ball in a circular path by spinning around himself and give the ball the maximum possible speed. Just before the hammer is released, it has a uniform circular motion. The uniform circular motion is a motion of the object with a constant speed along the circular path of the constant radius. Radius in this case is the distance from the ball and the spinning axis. Object that revolve about single axis undergoes a circular motion. For example, washer and dryer or merry-go-round. Anything that revolve around the axis undergoes circular motion. During the uniform circular motion, by moving the ball in a cycle, the athlete apply the force of tension in a wire which keep the ball in a circular path, so making the ball to undergo uniform circular motion. Otherwise, based on inertia, the ball will move at a straight line, so that tension in wire force the ball to undergo circular path. Based on the second Newton law, we know that force and acceleration are related. The bigger the force, the bigger acceleration. But this time we have a tension in a wire. So the greater the tension, the greater acceleration toward the center of the circle, and the faster the ball moves in a circular path. Now here is another experiment. When we tied up the bucket filled with water, halfway with water, and we have to use a very strong string or rope, because there's a lot of tension on that rope, and try to spin that in a horizontal plane. You're going to see the water will not spill, and we're going to talk more about that later on. But if you try that in a vertical plane as well, the water will not spill even if the bucket is upside down above your head, but you have to spin it fast enough so the string has to be tight. Another thing that is a warning is that you have to do that experiment. If you can't do that, you don't have to do that experiment, but you can do the experiment in a very safe place. Even accidentally you spill the water, should be in a safe place outside, for example. But one thing you have to keep in your mind, because there's a lot of tension in that rope, especially when the bucket is at the bottom and start to move up. That is the maximum tension in a string. So one common thing that they have, those objects move in a circular path, so the velocity constantly changes the direction, so they are accelerating. That is how the circular motion looks like when you see that from above in both those experiments. And if you draw the diagram of the velocity and acceleration, you see that velocity is a tangent to that line and acceleration is toward center. At any point is always pointing toward center of that circle. In order to derive equation for a centripetal acceleration, we have to review few things. First, velocity is a tangent to a circle at any point. So if you take a look on the diagram on the right, the velocity at point 1, for example, is tangent to the circle. At point 2 is a tangent at the circle at any point. Another thing is that might make easier for you is that velocity is a perpendicular to a radius at that point, and it is perpendicular to a radius to any point on that circular motion. So any point that the object is, the velocity of that object is perpendicular to a radius at that point and tangent at that point in a circle. So the direction changes constantly changes throughout that circular motion. However, the magnitude of velocity doesn't. So that's why sometimes instead of using velocity, we use speed as a terminology, because we know that velocity magnitude does not change, and we are well aware of the position or the direction of that velocity. So that's why we call that speed as a tangential speed, because the velocity is tangent at that point. The tangential speed is the speed of the object along the imaginary line that is drawn tangent to the object circular path. The object distance from the center of the circular path is constant, which is radius, in the uniform circular motion. So centripetal acceleration is due to change in direction, not the magnitude. So as we know, acceleration is about change in magnitude or direction or both. We know pretty sure now that magnitude does not change, but direction of that velocity change constantly to be tangent at any point where the object is in that circular path. Another thing is it is directed toward center, because change in velocity is directed toward center. If you take a look on this diagram, you see that anywhere that you can draw a vector v1 or initial velocity, or vector v2 or final velocity, you see that that is common is a tangent. They are tangent at that line. However, if you do based on what change in velocity is a final minus initial, that means that change in velocity always point toward the center, and that's how you can calculate acceleration. Acceleration is about change in velocity per interval of time. That is how we learn about kinematics, about change in velocity, but this time that acceleration is a little special, and we call it centripetal acceleration. Here are key concepts while we are deriving equations for centripetal acceleration. Acceleration is a rate of change in velocity. We know already. As the object moves from point A to point B, the direction of the object velocity vector changes, but magnitude remains the same. So that's why we use most of the time the concept of speed. For a short interval of time, change in the velocity is directed toward the center of the circle. That's where the acceleration direction is directed to. Now we're going to look at the similar triangles at the radius and the velocity. Take a look at the diagram. So in the diagram at the circle, when we have a radius R1 and R2, but since that is a circle, radius is the same. So this triangle that is made of two radius and a distance from A to B, it's triangle that has two sides equal. Now, what about the triangle with the velocities? So this is initial velocity or velocity 1, and this is final velocity or velocity 2. But we said already the magnitude of velocities is the same. So the magnitude is always unchanged. So this triangle has two sides that are equal. An angle between those two triangles is the same as well. Why? Because those vectors are perpendicular to a respective radius. As they are perpendicular to a respective radius, the angle between them has to be equal to the angle between two radius. So that's why we have two triangles with the same sides, equal sides, and the angle between those equal sides is equal to other triangle. So those two triangles are similar triangles. As a similar triangles, we can say the ratio between sides is equal to each other. So change in velocity over velocity, because we can not choose initial velocity or final velocity because the magnitude of those velocities is the same as we mentioned. So change in velocity over velocity is equal to that distance between A and B that we call sector over one side, which is a radius. So S over radius. Or if we have a very small angle, when the distance between A and B is very small together, that sector and the distance and straight line, delta D, is the same. So we can write, instead of sector, we can write delta D over R. But that delta D is equal to speed time time. So the distance is equal to speed time time. So that means we can replace that delta D here with V times delta T. Now take a look. We can switch places of the V and delta T. We take the delta T and move it down here, and we move V up. Then we get like this. Delta V over delta T is equal to V times V divided by R. So is delta V over delta T is a change in the velocity per interval of time. And then we have V times V is a V squared over R. Then now we can write that change in the velocity per interval of time is acceleration, but this time is a centripetal acceleration, which is a change in velocity per interval of time. But we already know that change in velocity per interval of time is a V squared over R. So we can write AC is equal to V squared over R. So centripetal acceleration is equal to square of speed over radius of that circle that the object undergoes in a circular path. Let's do some practice with the centripetal acceleration. At a distance 25 km from the eye or center of the hurricane, the wind moves at nearly 50 meters per second. Assume that wind moves at a circular path. Calculate the magnitude of the centripetal acceleration of the particles in a wind at this distance. So what do we have? We have a radius is 25,000, that means 25 kilometers. Change that in a standard unit. Speed is a 50 meters per second and centripetal acceleration is required. You can have the formula and you can plug numbers all in a standard unit. We have everything. So we have centripetal acceleration is equal to 0.10 meters per second square. Second, a jogger is running around a circular path that has a circumference of 478 meters. The magnitude of the centripetal acceleration of the jogger is 0.146 meters per second square. Calculate the jogger's speed in kilometers per hour. So what do we have here? Is a circumference 478 meters. Centripetal acceleration is 0.146 meters per second square. Speed is required. First, we need to solve for speed on the base formula that we have. AC is equal to V squared over R. We solve for V is the square root of AC R. And another thing is a connection between circumference and radius. So circumference is equal to 2 pi R, and we can solve for R is equal to C divided by 2 pi. Now we can solve for radius, which is 76.1 meters. Now we're ready to solve for speed, which is a square root of AC times R. So AC is 0.146 meters per second square. Radius we just calculated is 76.1 meters, and we get speed is 3.33 meters per second or 12 kilometers per hour. Now is your turn to practice. An athlete in a hammer throw competition swings the hammer with a uniform circular motion clockwise as viewed from above at a speed of 4.24 meters per second at a distance of 1.2 meters from the center of the circle. So that means radius. At a given instance, the hammer velocity is directed toward southward. Determine the centripetal acceleration at this instant. Now you have pencil, paper, calculator ready. Pause the video and start to do it. And if you got 15 meters per second square west, you did the right thing. Second one, a ball on a string moves in a horizontal circle of the radius 1.4 meter. The centripetal acceleration of the ball has a magnitude of 12 meters per second square. Calculate the speed of the ball. Pause the video and try to do it. And if you got 4.1 meters per second, you did the right thing. And the last one is suppose a satellite revolves around the Earth in a circular orbit. The speed of the satellite is 7.27 times 10 to the power of 3 meters per second, and the radius of its orbit with respect to Earth center is 7.54 times 10 to the power of 6 meters. Calculate the magnitude of the satellite centripetal acceleration. So pause the video and try to solve it. And if you got 7.01 meters per second square, you did the right thing. Now we know the equation for centripetal acceleration, but what if we cannot measure the speed? So equation is speed square over radius. So what happened if we don't know speed? Is any other alternative? Yes, we have. So we may be able to measure the time it takes for the object to move once around the circle, or period. So that period is a time of one cycle. Now we know that speed is equal distance over time, but in one cycle, one distance around the circle is 2 pi r, or circumference, and time for one cycle is period. So that means speed is expressed in a 2 pi r over t, and from the base equation, which is v squared over r, we can replace v with what we found as a 2 pi r over t. So we replace that v with 2 pi r over t, and we get 1 over r is equal to 2 pi r over t all in power of 2, which makes 4 pi square r square divided by r t square. So that square with the r cancel, and we got centripetal acceleration is equal to 4 pi square r divided by t square. Now we know that sometime we may actually just count the cycle per unit of time. So we can measure how many cycles or full rotation the object completes per unit of time, or what we call frequency of rotation. We know that a relationship between frequency and period is they are inverse of each other. That means we can use that equation that we just got about period, and we can replace the period with inverse of frequency, or inverse of period with frequency. So that means we can rewrite the equation 4 pi square r over t square to 4 pi square r over 1 over t square. And 1 over t square is f square, so square of frequency. That means we get a new equation. Centripetal acceleration is equal to 4 pi square r f square. So with those two, equation, we don't really need speed anymore. We can calculate that centripetal acceleration using either a period of revolution or frequency. Here's a practice problem involving period and centripetal acceleration. The planet Venus moves in a nearly circular orbit around the Sun. The average radius of the orbit is 1.08 times 10 to the power of 11 meter. The centripetal acceleration of the Venus has a magnitude of 1.12 times 10 to the power of -2 meter per second square. Calculate Venus period of revolution around the Sun in a second. So what is given is a radius and centripetal acceleration. The period is required, so we can use a formula that includes period, which is centripetal acceleration is equal to 2 pi square r over t square. We solve for t. 2 pi goes outside of the square root, so 4 pi square goes out of the square root in 2 pi times square root of r over ac. Now we are ready to plug those numbers that we already have, plug those numbers in the calculator, and find 1.951 times 10 to the power of 7 second. And then if we want to convert it in Earth days, then we can divide by 3600 to turn hours into a second. Then we can divide it by 24 hours. That has 1 day. So 1 hour has 3600 seconds. We divide it, and we can divide by 24 hours because 1 day has 24 hours. And we get 225.8 days or 226 days, like Earth days. Here's another practice problem. This time involves frequency. A research apparatus called centrifuge undergoes centripetal acceleration with a magnitude of 3.3 times 10 to the power of 6 meter per second square. The centrifuge has a radius of 8.4 centimeter, not meter, centimeter. Calculate the frequency of the centrifuge in hertz, so 1 over second. So we can calculate using that formula that involves frequency, which is AC is equal to 4 pi square r f square. So you can solve for f, which is square root of AC over 4 pi square over pi square times r. And then we plug those numbers. We have centripetal acceleration as 3.3 times 10 to the power of 6 meter per second square. 2 pi square times r is 8.4 times 10 to the power of -2 meter because it is in a centimeter. Then we plug those in the calculator and we have 9.96 times 10 to the power of 3 hertz. If we have to convert those in a revolution per minute or rotation per minute, we can make sure that it is per minute, not per second, as a hertz is per second. So it's a 60 second in 1 minute. We can multiply by 60 and we have 5.98 times 10 to the power of 5 revolution per minute. Now is your turn again to do some practice. Get your calculator, paper, pencil ready and pause the video and solve it yourself. The centripetal acceleration of the object at Earth equator results from the daily rotation of the Earth. Calculate the object's centripetal acceleration given that the radius of the Earth at equator is 6.38 times 10 to the power of 6 meter. Pause the video and solve it. If you got 3.37 times 10 to the power of -2 meter per second square, you did it right. And another one is a bicycle wheel with a radius of 0.300 meter is spinning clockwise at a rate of 60 rotation or revolution per minute. Calculate the period of the wheel's motion. Calculate the centripetal acceleration of a point on the edge of the wheel if at the instant it moves westward. Pause the video and solve it. And if you got for A 1 second and for B 11.8 meter per second square north, you did the right thing. And we reached the end of the lesson. Have a good one.